Hi again. Okay, this is going to be another part of the same problem that we were solving before. There was one viewer that said, "You drive me crazy when you drink. The way you drink. This is for you to drive you crazy." Okay, so in the other problems, in the first part of the problem, which I just did it in two different ways. The first part of this was a what is it here. That's the second part. That's the first part. Yeah, this was the first part. It was just calculate reactions at A and B, and then we did it. This is the first part, the first approach, which I call the brute force approach. Now the second approach for that was this one. Was this part here, and then I call this the equation approach, which is the same one. 4 reactions. Now we are asked in this part to calculate the shear at C. Do you remember how to erase that part? You should remember how to, but in case that you don't remember how to, I'm gonna tell you. How do you calculate the shear at C? How do you calculate the moment at C? You have to make a cut. That's exactly what you do. You make a cut at C, and then you separate that beam, that structure, in 2 parts. If you use this part, you're going to have here your AY, and in this other side here, I'm gonna put it here, even though I don't like it too much. Yeah, I'm gonna put it here, and then you have the By is acting here. Remember, internal forces. If you use this side of the beam, the correct direction for the shear is going to be like this, and the moment direction is going to be like that. Now, for the other part, the correct direction, the convention that we're using for shear is that, and the direction for the moment is that one over there. Now, what happened here, in case that you haven't still thought about it, which you should, by the way, completely and totally, is we have a moving load, and that moving load is changing. That moving load is changing and is moving, changing positions here. So at some moment in time, the load is going to be here. The moving load is going to be there. But after that, the load is going to be moving to this other part of the beam, to that other part of C. And what that is telling you is that we have to differentiate between this and between that, because if you remember, reactions are reactions, but in the case of the shear here, the shear switches position, there is a jump in the switch, in the shear, whenever you have a concentrated load applied, a shear load applied to it. So that's why you have to be really careful when we do this. So let's first start from the general method, and let's say that I want to apply a unit load here, and this is the distance x, and then I'm going to calculate the reactions. So that will be the first part of this problem, calculate the reactions. Then if I do summation of moments at B equals 0, like that, I'm going to have that AY times 8, negative 8 AY plus this distance, and that distance is, well, if this is 1, if this is x and this is 8, that distance is going to be 8 minus x. 8 minus x times 1, which is the load, equals 0. And then I can solve for AY. I pass this to the other side. 8 divided by 8 is 1. 1 minus 1/8 of x. And we knew that. And we know also that the reaction at By is 1/8 of x, because we calculate them before. And if you didn't get that video, watch it. But if you didn't, if you do summation of forces in y here, 1 minus 1 minus this, it's going to be basically that for calculating By. So we have the reaction now. But it's going to be a completely different scenario for the shear when the load is here, when the load is there. So this distance from here to here is 4 meters. And this is going to be our first interval. We have to do this in intervals. When the load is moving in the first part, x is going to go between 0 and 4. So what happened here when the load is between 0 and 4? The load is there. If I want to calculate the shear, what do? I do summation of forces in y equals 0. So you have AY minus BC minus 1 equals 0. And then if you know AY is that over there, or you can say BC is equal to AY minus 1, or you can say BC equals 1 minus 1/8 of x, that's AY minus 1, or BC equals negative 1/8 of x. That will be the value for BC when you are in this interval. Now once the load is, there are two ways of doing this thing. I like the easiest way. But I'm gonna, I don't know, complicate you at this level. But no, I'm gonna show you the easy way, and maybe I discuss the other way, but just show you the easy way. Now the other interval is between, when the x is between 4 and 12. So 4 smaller or equal than x is smaller or equal than 12. But that is the situation. This load 1 is not here now anymore. Now the load 1 is going to be somewhere in this part. That's going to be the load of 1 over there. Question. And of course I am expecting an answer, but you know, I'm working on my mind reading capabilities and long distance reading, but I'm not there yet. So I'm gonna imagine that you answer to me. But the question is this: this shear and this shear are the same? Why not? No, yes they are. I mean, of course they are. This shear and this shear have to be the same. The convention is different, but the value of the shear is always the same. Why is the reason for that? Because we are at the same point and we don't have any concentrated force applied at that point. So if this shear is equal to this shear and the load is here, there are two ways of doing that. First, the easy way, which is the one that I like and a bunch of people don't. I don't know why. If the load is here, I don't care about the load anymore if I calculate the shear in this value of the shear, because the load is not there. So I can use the first part, this part. I'm studying when the load is here. I'm not changing this. But if the load is past that point, and I can use this to do summation of forces in y equals 0, and say AY minus BC equals 0, and say BC equals AY equals 1 minus 1/8 of x, why any people in their sane mind is not going to use this thing which is so easy to do? Now this is the correct, fast, smart approach. Now what is the not very smart approach, but it's a valid approach also? Using this side to calculate the shear. But if you use this side, then you have to imagine that from this point to there is going to be x, and then you have to do well, actually in this part it's not gonna be so much of a difference. I'm going to the other part, which is the moment already. I'm thinking of moment. So for the shear it's almost the same, but not for the moment, even though it's easier for here. But if I use the other approach and I use this part, I could say also that if I use this part of the beam, I can say summation of forces in Y equals 0 on this side, and then I say VC minus 1 plus Vy equals 0, and Vy is this one. So when you put here Vy 1/8 of x, then Vc is going to be equal to 1 minus 1/8 of x, which is the same value that we got using this side. And it has to be the same value. Now, I was going too fast with my thoughts, and I was referring to the moment, because for the moment the equations are huge when you do the other approach. But in the shear, yeah, try to get used to that. Load is here or load is there, load moves. So which one of both? Either is going to yield the same result. Now what do you do with this? Now we have to create a table for that. Let's create a table. I'm going to use a second paper, kill another 3. And I'm going to put here x and VC. And then we're going to go through several values. I'm going to give the same values that I gave before for x. But there's a slight difference now. Because the first value was x equals 0. And the second value that we used was when x equals 4. But when x equals 4, we're exactly on top of C. And you know what happened with the shear on top of, when you have a value of the concentrated force on top of the shear, it's going to jump. So basically, and by the way, you have two different approaches, two different equations. Here is 4, and here is also 4, these two limits. So what you have to do here is 2 times calculate that value. And you say, I'm going to calculate it when the load is to the left of the point C, or I'm going to calculate it when the load is just on top of the point, but it's just passing the point and it's moving to the right. And then, in other words, you're going to do it when the load is here, 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 and there. That's that point. And then immediately it's there, then you're going to move to this other side. So it's the same point. You have to do it with the new equation and keep moving the load over there for 8 and for 12. This part, all of these values have to be calculated using this equation for the shear. Uh, 1/8 of x. And this other part is going to be calculated using this equation, which is the same equation. Vc equals 1 minus 1/8 of x. Now let's do that. If I put here 1/8 of 0 is 0, so that's what is going to be 0. If I put here 4 in this part, when it's approaching, and this is negative, by the way, right? Yeah, this is negative. Oh, good catch, good catch, good catch. I realized it because the shear had to be negative at that point. Okay, negative. This is 1 minus 1, negative, and this is 1/8, yes. And you didn't tell me anything, and you were watching that thing. Okay, so negative 1/8 of 4 is negative 0.5. Right there, negative 0.5. Now I switch to this side. When I switch to this side, then you're going to have the equation is going to be 1 minus 1/8 of 4, same value here. So this is going to be 1 minus 0.5 equals 0.5, 0.5. And then when you're here, you keep using the same equation because you are in that side. 1/8 of 8, so 1 minus 1 is 0. And this one is 1 minus 1/8 of 12, which is negative 0.5, negative 0.5. And we have our values for the shear. So what is the next step? The next step is plot it. Let's plot the shear. Plotting the shear. I want to do this. I'm going to put here my AY, my BY. and this is my thing's gonna be here. This is gonna be my axis X, and this is gonna be my shear. Now the point C is here. This is a little bit off the scale, so let's cut it here. Trim that part. I don't have whiteout. If I have whiteout, I will put it there, because that's gonna keep bothering me for a long time. So you know something? I'm gonna use old school whiteout, and I'm gonna put it there. Old school whiteout. Old school whiteout. This is old school whiteout. There you go. The only thing that I need to put there is a little bit of glue. That's what I used to do for whiteout. Okay, there you go. Now if you put the table, the values for the table, when x equals this, when x equals 0, this value is 0. When x equals 4, this value is negative 0.5. Negative 0.5. Now, at the same point, when x equals 4, which are here, the value is 0.5. Now, when x equals 12, this is 0. And when, 8. And when x equals 12, you are at the other end of the spectrum here. And the value here is negative 0.5. Negative 0.5. Like that. So that means that your shear influence line is going to be something like this. Straight line. Remember, I'm sorry, straight lines all the time. Like that. And then in this other part, it's going to be like that. Like that. This is the influence line for the shear acting here in this part. Now look what happens again. This is not shear moment diagram, but exactly this is the opposite, because these reactions are the opposite. The unit load is here, it's supposed to be here, right? Look at the difference between these two. 1. That happens because you have the unit load and then you have the reaction of the shear in this part, but this total distance should be 1 and they are 1. Now same. If you are, for example, designing stirrups, I don't know, or designing something where is going to be the maximum shear happening in that element, you can calculate it with this. In the case of shear, within my applications at least, positive or negative doesn't make a big difference. But the absolute value is very important. The only difference between positive or negativity of the shear is when you go and you use it for calculating the moment. Okay, shear at C, done. I hope that you liked it. I liked it, and I keep liking it. Thank you for watching. Thank you for learning, and I see you now.